Good day, physics students. I apologize for the last minute change and last minute atypical sort of setup. This video will be kind of take the place of the main part of today's lecture. It's just going to be me going over the rest of the information from the rest of the chapter 16 notes. There's not a whole lot more to go through. We're just going to look at a couple more formulas and a couple more examples, some of which will actually be a review from last week's lab, thankfully. Last week, week before last, the capacitance lab. Some of it will be from the capacitance lab. For a lecture on Thursday, your instructions are to watch this, and then I will have open Google Meet class calls that I'll be in for students to hop in and hop out of if they have questions during or after the videos. You don't have to necessarily join them if you feel like the video was all that you needed and you feel like you can finish up all the assignments from there. Then attendance in them is completely optional. But I will still be in the calls during our normal class times. So that'll be 10 to 11 a.m. and also 12 through 1:15 p.m. I'll be in them for when class would normally be so that you can drop in during normal class time if you have anything you would like to specifically address. This little recording should close out most of chapter 16. So if we meet back in person on Friday with e-lecture, and when I meet back in person with all classes next Tuesday, we'll take a minute to re-summarize everything, open up with any questions that you have about the homework and quiz, and then move on to chapter 17. If you have any questions, please email me at any time or jump into the calls tomorrow. And let's go ahead and move on to the notes. I'm going to be uploading a newest amended copy of the notes, which has some more examples and has some things in it that I've already worked, since I'm not going to be there to write it on the board. And I recommend you go along with those notes as I'm talking with you here today. Real quick, I'm actually going to try to I should have tried to find this before starting the recording. Sorry about that, everyone. I recommend you follow along with the slides as I'm showing them. Have them up on your screen. And I just put slide numbers on all of them so that you can see which slide I'm on in the video, and so that you can, I'll say it out loud so you can be following along as well. So, whoops. We have talked a lot about what the capacitor is physically, how does it work, the things that go on inside of it, the formula for finding the, this formula, whoopsie. These formulas here, this one formula actually is for, if you know the capacitance of the capacitor, it will hold a specific charge based on the current voltage it is exposed to. This is a model of a capacitor from the inside. One formula, though, that is kind of slipped, that I have yet to mention, but is one that you will need for your homework and quiz, is this formula here is capacitance as a function of the charge on the capacitor and the voltage it is exposed to. These all happen after the capacitor has already been built, after the physical object has been plugged into a circuit. There is a different formula for what to do if you are building the capacitor yourself. It's not in a circuit yet, but you know its physical characteristics. We have this formula here. The formula is capacitance of a capacitor is equal to the permittivity constant. That's I believe that's the letter C. Wow, I've completely forgotten any Greek alphabet that I ever knew in this moment. That little Greek letter there with the 0 subscript. That is a constant for the permittivity of free space. I'll get more to that in a second. It's a known constant, though. You can see the value that you would plug in for it right there at the bottom. Capacitance of a capacitor is equal to that permittivity times the area, the surface area of both of its plates. What I mean by that isn't that you need to add the two areas together, just that the two plates need to have the same area, and that whatever that area is, you would plug it into that part of the formula. And then you divide by d, that is the distance between the two plates. If you'll remember from the capacitors virtual lab that we did, we had a capacitor manipulation tool, very similar to the one you can see, the screenshot you can see on screen right now, where you can manipulate the plate area, the separation between the two plates, etc. And we saw that those two factors affected the capacitance of the capacitor, and this is the formula for determining how. The constant that's in there, the permittivity constant, summarizes a couple of things. The area of the plate and the distance between them is handled by A and D, so the permittivity constant handles a couple of things together at once. It handles the properties of the electric field contained within the capacitor, and it handles, additionally, the rate at which electrons will flow through the capacitor. This constant is called the permittivity constant because the material between the two plates determines how fast electrons are permitted to travel from one plate to another. We mentioned previously the concept of a dielectric, which is to say that some capacitors have some specific types of materials literally put between these two plates, sometimes to help keep them from touching, sometimes to make sure that it has a certain end capacitance, and that this permittivity constant is what factors that in. Every different material that you can put inside of a capacitor would have a slightly different permittivity constant because different materials permit electrons to flow through them at different rates. This value right here, permittivity of 8.85 times 10 to the negative 12th farads per meter, that is the permittivity of air. So all of the capacitances that I will give you to calculate with this formula, we're going to assume that there is nothing but air between their two plates, only air. In real life, usually there's some material other than air between those two plates, but for simplicity's sake, we have this one permittivity that is generally accepted and comes up a lot in physics. This constant is used in several places. We are going to stick with air for any problem. So you can write down permittivity, and you can put, I recommend putting next to it, of electrons traveling through air. But that is everything you need to be able to find what the capacitance of some capacitor you have built is. So, with that in mind, using that previous formula, what should the capacitance of the capacitor on the right be? I'll give you guys just a second to calculate that. Okay, and the answer I'm getting is 2.058 times 10 to the negative 13th. The reason I'm getting that is the numbers listed here, the 8.6 and the 200 are in millimeters or millimeters squared. Do make sure to convert those to regular meters first before proceeding. If you didn't convert them to millimeters, though, the power of the answer would be the only thing off. The main number itself should still be about 2.058. Next question, assuming said capacitor, the one built here in the picture, is attached to this 1.5 volt battery, how much charge should it hold? For that, we're going to scroll up real quick to slide 12. Capacitance equals charge divided by voltage. We have our 1.5 volts. We have the capacitance we just calculated. So in that moment, we should be able to find how much charge this capacitor would hold in this circuit. And the last sort of concept question here. Based on the formula from the previous slide, what effect would doubling the surface area of the plates have? So looking at the formula, if A, let's just say that we plug in nothing but ones here. So 1 equals 1 times 1 divided by 1. If we doubled the surface area and say plugged in a 2 instead of a 1, then as a result, capacitance would also become 2. Capacitance would double if you double the plate surface area. So in general, capacitance is directly proportional to plate size. Then, what would doubling how far apart the plates are do? If we switch everything back to ones, 1 equals 1 times 1 divided by 1. If D was twice as big, it's in the denominator, then capacitance would go down by half. So it would be twice as small. Notice a lot of the formulas we talked about this year, if there's a distance term in the bottom, it's usually squared, meaning that the distance tends to mean a little bit more than the other terms. That is not the case here. It's not squared in this one, so it's just a linear change. If you double the distance between the plates, then the capacitance will be divided by 2. If you make the plates 2 times closer together, then capacitance will just be doubled. So things to keep in mind. Now, this simulator you should have seen during last week's lab. And similarly, last week's lab we also looked at how capacitors function in circuits. Now, the physical capacitor is a component that can be plugged into a circuit. Things that it can do while plugged into a circuit include, but are not limited to, acting as a battery in some situations, since it can store up charge and energy and then discharge it later. It can redirect current from one part of the circuit to the other. Once it becomes charged, it might block current from going in one direction, whereas it lets it through if it's not currently charged up. They have a lot of uses, including like the TV vacuum tubes and the old touch screens that I've mentioned before. And we're going to be looking at a lot more circuits moving forward. Next week, we're going to start talking about resistor circuits as well. And so in circuit diagrams, since the diagrams themselves are all just shorthand, there's different symbols used for everything. So these are the symbols within the drawings. Battery is represented by 2 parallel lines of different lengths, and occasionally a plus and a minus are drawn in for a little benefit to help make sure it's clear what the battery is. The symbol for capacitor in all these drawings is 2 parallel plates that are the same width, which thankfully ties into what the capacitor physically is. So if the 2 plates are parallel to each other and the same length, that is the capacitor in the circuit. And right here on slide 18 is kind of a sample circuit diagram using less of the symbols and more of actual object stand-ins. In order to have a circuit, you're going to need some battery or some voltage supply, because voltage is like the water pressure that drives the current. The battery itself needs different amounts of potential on one side or the other. And that difference in potential is the battery's voltage. And that voltage is going to push electrons through the circuit. So electrons are going to try to get away from the negative end of the battery, travel through this wire. They're going to travel through this capacitor, then through this capacitor, and then back to the battery. In order to have a complete circuit, you do need one continuous path from one end of the battery, uninterrupted, to the other end of the battery. A lot of things can happen to that current along the way, but there still has to be some pathway for it to follow to be able to get back. Otherwise, you won't have a circuit. Now, the type of circuit pictured here is a series circuit. We have a battery, and then we have two capacitors wired into the same circuit as that battery. And those capacitors are wired one after the other. Any electricity that goes through this first capacitor has to also go through the second capacitor before making it back to the battery. This is what defines a series circuit, because these elements are literally in series. They are one chained right after the other. And in order to find, well, when you put multiple capacitors together in a circuit, they tend to work together in interesting ways. If you wanted, just a 100 farad capacitor for your circuit, you could put a 100 farad capacitor in your circuit, but sometimes if you don't have the right capacitor size on hand, you can plug in multiple capacitors together and they will add up to a different but desired total sum. And the way that the capacitors add up and work together depends entirely on what type of circuit you're making. This is a series circuit, and in a series circuit, the total sum of the capacitance is a little interesting in order to calculate. We've got two capacitors here in this situation. Excuse me. Capacitor 1 and capacitor 2. And they're in series. They're working together, contributing to the total capacitance of the circuit. The formula for determining that capacitance is 1 over total capacitance is equal to 1 over C1 plus 1 over C2, and the plus ... refers to there could be, any circuit could have more than two capacitors. If there was 3 or 4 of them in a row like this, then you could do 1 over C1 plus 1 over C2 plus 1 over C3 plus 1 over C4 for as many capacitors as you have. You are adding the reciprocals together, and then you are taking the reciprocal of that reciprocal sum. The ultimate effect this has is if you wire a bunch of capacitors together in series, that's ultimately going to drive the entire circuit capacitance down. Because since they're all in a row, they're all sort of fighting for the same current, for the same charge source, and they end up sort of working against one another in that way. This is one of the two major types of circuits, series circuits are, and they're very common because they're very easy to make. You just wire everything up end to end. The problem with a series circuit, and I trust that this is review for a lot of people, the problem with a series circuit is if there was a cut in this wire right here, then suddenly there's no path for the electrons to flow through to get all the way through the circuit, which means the circuit just dies. The whole thing goes dead just because there was one cut made right here. This is the type of circuit that old Christmas lights were. One bulb goes dead, the whole circuit goes dead. They are very inconvenient for quality of life and keeping on your light bulbs in case one of them breaks situations, but they are useful in case you actually want a system to go down if some part of it fails. There are definitely very specific situations like with fusion plasma experiments where if something goes wrong, you want the whole system to shut off in that exact moment. So we'll talk more about some of the benefits of a series circuit next week. For right now, the main benefit, the main trait of this configuration is every element is listed one after another, and if part of the circuit breaks, the whole circuit dies. This is different to a parallel circuit. This type of circuit is defined by the fact that current coming out of the battery can go down one of multiple pathways. So following current out of this battery here, we're traveling out, we hit this particular branch right here, and current can either go down this pathway or down this pathway. But the currents are going to come back together at this other junction and then go back into the battery. The current will still end up in the same place, but it has to pick one of these paths to go down, and it can't go down both of them on the same lap. current only flows in one direction. So if current goes through this first rung here, it's not going through the second rung during that same lap. So parallel circuits will split the current because literally some of it will go to the left and some of it will go up onto the next part. And what's interesting about capacitors wired in parallel is that they end up working together and adding up linearly. So we have C1 and C2, and if we wanted to know the total capacitance of this entire circuit, we would just add them together. The total effective capacitance of this entire circuit is just the sum of C1 and C2. So capacitors in parallel work together. That's one of the features of capacitors in a parallel circuit. And one of the main features of a parallel circuit, period, is that, say someone were to take some wire cutters and cut the line right here. That would eliminate this branch of the circuit as an option for electricity because the electricity couldn't get through the break, but the other pathway would still be open. So even if I made a cut here, there would no longer be any electricity through C2, but electricity could still flow through C1 and keep going. So parallel circuits are neat because if one element goes out, the whole thing can still keep running. This is what most modern Christmas lights are based on. If one bulb goes dead, it's actually in parallel with all of the other bulbs, and so the other bulbs can still stay on. So let's just look briefly at a couple sample questions here. This is a parallel circuit, and we can tell because the current comes out of the battery, it hits that fork, that crossroads there, where it will go down one of 4 different paths. We have 3, 6, 12, and 24 microfarads before joining back up and then heading back to the battery. These are in parallel, so excuse me. Even lecturing remotely, I end up yawning and needing water. Because they're in parallel, the thing we're going to want to do, the thing we're going to want to do is add them together. So parallel capacitors are going to add up together linearly. So the sum of 3 and 6 and 12 and 24 is going to be 45. Just add all 4 of those numbers together. Next, we have a series circuit. And we know it's a series circuit because all the capacitors are listed one after one another. The current has to go through all of them in order to get back to the battery. And here, instead of adding them all up directly, we need to take the reciprocal of the sum of the reciprocals. I invite you to take a second, maybe pause here to work that out for yourself. Once you've done that, the answer will be right here on screen. As a result of being a series circuit and the way that they add together, you should be getting 1.6 microfarads. If you're not able to get this number, please let me know. You can hop into the call. We can work it together, or you can email me about it. Now, the last thing I want us to look at together is something that throws people for loops all the time. Doesn't matter what type of circuit I'm teaching, capacitors, resistors, etc. Combo circuits like this one always throw people for a loop because they're all different. They all kind of require their own unique strategies. And this one itself is, I call it a combo because it has pieces that are in parallel but also in series. So, let's just look at the circuit as a whole here. We're treating this as sort of a part of a larger circuit. Current's going to come in through A, travel through the whole thing, and then travel out through B. As the current comes out from A and travels through, we're going to hit this junction right here. Current can at that point either go down this left pathway, where we travel through C1 and then C2 and back out. We could also either go just through this C3, or we could go through this other C1 followed by a C2 before we merge back together. So that tells us this chunk right here is 3 different parallel branches, but 2 of those branches have 2 capacitors in series on them. So both of these pairs of C1s and C2s are in series with one another. I want to go ahead and address something. Just because 2 things are, on physically drawn parallel lines from one another doesn't make them part of a parallel circuit. The C1s here are, parallel to this C2 in terms of the drawing, but in the actual circuitry that would follow, they are in series because the current's going to come here, go through C1, and then go through C2 before remerging back up here after all the other splits. So don't look at it in terms of is it drawn parallel on the picture. Look at it in terms of how is the current going to flow in this situation. So we've got one parallel branch here that has C1 and C2 in series, one parallel branch that is just C3, and one parallel branch that has C1 and C2 in series. The currents are going to meet all back up at this point, continue on until they hit this junction where they're going to split again. This is a pair of parallel capacitors. Some are going to go through this leftmost C2, some are going to go through this rightmost C2. After those points, they're going to come back together, remerge, and then continue on to B. Now, the answer is already on screen. It's in the notes, so I'm not going to hide it from you. In fact, I have actually included my work in finding this on the next couple of slides. My advice for all combo circuits, no matter what kind they are, because we're going to see more later, is to work it from the inside out. There's no one formula that you can plug this whole thing into right off the bat that will give you the correct answer, because there's both series and parallel operations going on in here, and there's no one formula that does both of those at once. You're going to have to do each rung, each piece, one at a time. And I show those steps on the next couple of slides. If my handwriting is just completely illegible, please let me know and I will remake it, rewrite it, or try to decipher it for you. I've redrawn the circuit and I've filled in all of the numbers. And I've labeled the first 3... Excuse me, I'm terribly sorry. I've labeled the first 3 branches we're going to look at. A branch consists of this 5 being in series with this 10. B branch is this 5 being in series with this 10. And then the C branch is these 2 10s being parallel to one another. Looking at A, we have a series of 5 and 10. These are in series with one another. And you need to work these one rung at a time. You want to try to compress each rung down from multiple capacitors into just one capacitor. If you look at A and B specifically here, A is parallel to the middle one, which is parallel to B, but because there's multiple elements on A and B, we can't just throw them into a normal parallel equation. We have to figure out what this whole branch is, and then what this whole branch is, and then make this branch parallel to the middle, which is parallel to branch B. So for this branch, we have a 5 microfarad in series with a 10 microfarad. So we perform our usual formula and our usual operation, and we should get the total capacitance of just this branch as 3.3 repeating microfarads. B is made up of the same capacitors in the same configuration, so B will also have the same capacitance, 3.3 repeating microfarads. And C is the only part at this stage that's any different, because these two 10s down here are parallel to one another. We know this because the current's going to get here and split before traveling through each of them, only one at a time, and then remerging. So these 2 10s are in parallel. We perform our parallel operator, which is to say we just add them together and we find 20 microfarads. Now that we have these 3 numbers, we can replace all the elements we just used with these numbers that they are equal to. So watch the drawing very closely. A branch is equivalent to 3.33, B branch is equivalent to 3.33, and this C branch down here is equivalent to 20. So I have redrawn the entire thing based on that. I've gotten rid of A branch and replaced it with the number that A branch is equal to, same with B branch, and same with C branch. So, now that we're at this point, we have three things in parallel with one another, and then, after that current remerges, it is then in series with the 20. We can't do anything about that just yet. We've got all these things that are in series with the 20. We need to figure out what these are equal to before we can perform the series operator between this bit and the 20. So looking at this bit, we have three things in parallel to one another, 3.3 repeating, 2, and 3.3 repeating. So we perform our parallel operator, and we get that this whole chunk, which I have labeled D, should have an effective capacitance of 8.66 microfarads. So we can replace this whole thing with a capacitor of 8.66. We've reduced it from 1, 2, 3, 4, 5, 6, 7 capacitors down to just 2. And now that it's 2 capacitors in series, it's just a small matter of plugging these two numbers into our series operator and finding the total capacitance of the entire circuit. So combo circuits. So combo circuits always need to be worked one step at a time. And your goal is to start combining terms together so that there's fewer terms, fewer elements in the circuit, and ultimately that will create a more simplified circuit that will be easier for you to look at and find the total capacitance of. A couple of examples have already been worked about that on the lab last week, and also there's some on the homework as well. So if you're having trouble with them, please let me know. The combo circuits are kind of inherently tricky. They're puzzles, which I like. I like puzzles, physics puzzles, but I understand that not everyone does. So if you are having issues with them, please let me know. But that is the end of everything that you will need from Chapter 16 notes on the current Chapter 16 assignments and also for the exam at the end of the term. So, with this information, be looking at your homework. Start working on it, or continue working on it, because you've definitely already started like I asked you to. Sorry, I shouldn't guilt trip you guys. If you haven't yet, that's okay, but do please be working on it. Because the sooner you start it, the sooner it is to continue it and finish it. And if you have any questions about anything in these notes, you can hop into the class calls today or email me, and I will see you guys very soon to help further answer any questions you have. But that is all the material you will need for Chapter 16. So, lost my train of thought there. Sorry, guys. That just seems to happen every single time. Hop into the calls if you have any questions. I will be here during our normal class times today. Just let me know. And thank you all. I hope to see you again in person soon, and have a wonderful day.